All right, the next three examples are all going to revolve around the idea of what are called fundamental trigonometric identities. All right, these identities are just built off of all the relationships that we found before for sine, cosine, tangent, cosecant, secant, and cotangent. The fact that the sine and cosine are the y and x values, the tangent's the y over the x, the cosecant is the radius over the y value, secant is the radius over the x value, and cotangent is the x over y value. Now, I'm using the table they have in your textbook from section 4.3 right now, and it has the opposite and hypotenuse stuff written in here, just as a visual, but what I was just referring to was the table that was way back in section 4.2 on page 271, the one that has the y and the x's and all that stuff going on. All right, so in here they've thrown a bunch of things that they state as identities, and these identities are more or less just stuff they've built out of the basic building blocks of your trigonometric functions. Okay, since, like for instance, the sine of theta is equal to 1 over the cosecant. All right, they created this because we know the sine of your angle is equal to your y value over your radius, right? Your y value over your radius. The cosecant is equal to your radius over your y value. Now you can solve this equation for r if you wanted to. If you multiply both sides by y, you would get r equals y times the cosecant of theta. And since this denominator right here is equal to r, you could substitute this in here, which would leave you with the sine of theta is equal to y divided by y times your cosecant of theta. And as many of you probably already see, the y's divide out, leaving you with a 1 in the numerator. And all of a sudden, lo and behold, you've got the sine of theta equals 1 divided by the cosecant of theta. So there's all of a sudden this relationship that we can develop from the sine and cosecant. All right, the sine of theta is equal to 1 divided by whatever the cosecant of theta is. And this same relationship, all right, can be extrapolated for all the rest of these, all these reciprocal identities. All right, you could do the exact same thing with cosine and secant, and vice versa. And same thing for cosecant and sine over here. Cosecant equals 1 over the sine. If I had instead solved this equation for y and multiplied by r on both sides, I could substitute r times the sine of theta in here, and no, actually, now that I'm thinking about it, I couldn't do that. My apologies. What I meant to say was if you multiply both sides by r, you could substitute r times the sine of theta in the denominator right here for y because it's equal to y, and then the r's would cancel and you'd get cosecant of theta equals 1 over the sine. It all works out for the reciprocal identities in that same sense. So the idea is that each one of these trigonometric functions can be related to another one or a different one through a reciprocal identity. Now, the quotient identities and the Pythagorean identities are more relationships that we can relate these to based on other experiences in the past. The tangent and cotangent identities lie entirely in the fact that the tangent of your angle is equal to the y over your x. And since the sine of theta is equal to y and the cosine of theta is equal to x, you can substitute for y and x right here and get the sine of theta over cosine theta. So tangent is equal to sine over cosine. And same thing, the same kind of substitutionary method can be used to figure out what the cotangent is. Since cotangent is x over y, you put cosine in for x and sine in for y, and you get this relationship that's formed here. Now, the Pythagorean identities at the end here are all based off of the idea of the right triangle in your unit circle. If your angle is here on the, let's say here's your y-axis, here's your x-axis, here's your point, the circle's going around over here through that point and down and around, you get the idea. All right, the whole idea is that this side of your right triangle would be equal to the y value, and this side down here would be equal to the x value of this particular coordinate over here. And this is going to be equal to the radius, which in the unit circle is always 1. And the Pythagorean theorem states that a squared plus b squared is equal to c squared. You're going to get x squared plus y squared equals 1 squared. And that's actually where they get the equation of the circle from, the equation of the, in general, the equation of the unit circle. X squared plus y squared equals 1 squared, or the radius squared. But in this particular situation, this equation that we know is true based on the Pythagorean theorem, again, we can substitute in for x and substitute in for y, because x equals cosine of theta, y equals sine of theta. So if you substitute these in, all of a sudden you're going to get cosine squared plus sine squared equals 1 squared, or just 1, because 1 times 1 is 1. All right, now they reorder these to make it sine squared plus cosine squared, but it really doesn't matter which order you go in. It could be sine squared plus cosine squared or cosine squared plus sine squared. It's the same thing. You've got addition going on, okay? And then they can actually extrapolate these other two Pythagorean identities based on this identity. The idea is if you divide both sides of the equation by either the sine or the cosine, you can arrive at this. If you divide both sides by sine, sine squared over sine squared equals 1. Cosine squared over sine squared is going to end up just being the cotangent squared. And then 1 divided by sine squared is cosecant squared because of that. Now, let me talk about sine squared and cosine squared, like squaring all this stuff and what this all means real quick here. Because there can sometimes be confusion with that. All right, there's a big difference between sine squared of theta and the sine of theta squared. All right, those are two completely different things. This sine squared of theta is actually just another way of writing this. The sine of theta, whatever that equals, quantity squared, aka the sine of theta times the sine of theta. All right, so sine squared theta is equal to this, which is equal to this, sine squared times sine, or sine times sine. The sine of theta squared, that is the same thing as the sine of theta times theta. That's a totally different expression than this. Okay, in this you are multiplying the angle by itself and then taking the sine of it. In this you are taking the sine of the angle and the sine of the angle separately and then multiplying the results together. Totally different results. Okay, so that actually is written out in a remark in your textbook on page 280, just as a reference. Okay, so that is the case here when they refer to sine squared theta, this little square here. The reason they put the square up above the sine and not above the theta is to avoid this confusion. All right, if you put the square out here, it makes you think you got to do order of operations first. You got to do the theta times theta first and then take the sine. But you need to have the square in here with the sign, or it has to be written like this, sine of theta quantity squared, so you know that you're dealing with sine times sine. Okay, so to revisit the Pythagorean identities, when you get this, I said that you can divide both sides of the equation by sine squared, and cosine squared over sine squared was equal to cotangent squared. Well, that's just because, well, when you have cotangent times cotangent, if you multiplied both sides of this by cotangent, cotangent is equal to cosine of sine over sine, so you could replace the, if you set cotangent on this side and cotangent on this side, you could replace this cotangent of theta with a cosine over sine. And then you'd have cosine times cosine over sine times sine, which gets you cosine squared and sine squared. And the cotangent times cotangent gets you cotangent squared. So this identity applies to not only cotangent equals cosine over sine, but also to cotangent squared equals cosine squared over sine squared, cotangent cubed equals cosine cubed over sine cubed. It keeps going no matter what power you're dealing with. And actually, that applies to all these identities. The sine squared equals to 1 over the cosine squared theta, cosecant squared of theta. Cosine squared is equal to 1 over secant squared of theta, and yada, yada, yada. So you get the idea. All right, so this identity, the 1 plus the cotangent squared equals cosecant squared, can be arrived at when you divide both sides by sine squared, which, when you apply the same thing to both sides of the equation, it remains equal. To get the 1 plus tangent squared equals secant squared, you just take this identity and divide both sides by cosine squared instead of the sine squared to get to this one. And that's how all these identities are arrived at. Okay, now we're going to have to apply these identities to the next 3 examples in our slides.